Now we will discuss about the electromagnetic induction, okay, about how the force is acting when you are taking a charged bodies like this current carrying wires inside a magnetic field, of which around that we are having a magnetic field is coming, and that magnetic field interacts with the outside external magnetic field, and there is a force is acting there. Now we will see about a straight conducting wire, of which we are having the force acting on that we got is F is equal to BIL, when if you are taking a current carrying wire with a single wire. Now what we are doing is, at a time we are taking total 2 wires here. So taking 2 wires means in a plane of which we are having the magnetic field is present into the plane like this. Now we are taking 2 wires now at a time, of which 2 conducting wires you are taking. Okay. As you are taking 2 conducting wires here, let us suppose in both the cases, if the current carrying is going upwards here, the current is going upwards, then how the force is acting we will see. Now as the current it is going upwards here, then what happens there is, according to following the grip rule, actually here the magnetic field we are taking is the current carrying wire, which is taking into the thumb here. Okay. Whenever if you are curling that fingers around that conducting wire here, the curling fingers, if you suppose if you are taking that is out of the plane here, then the magnetic lines of forces around that are like anti-clockwise direction, that is means like this they are. Okay. That is for the first wire we have. Let us suppose this is the wire 1 and this is current carrying wire 2, that is. As you are taking in the first case, we are having that current carrying wire is like this, the magnetic lines of forces are present around that, and in the same way the second one, actually that is also we are having the same direction, that is again it is going out of the plane there, so that the magnetic lines of forces around that is also similar way we are having a anti-clockwise direction is present. So means even for the second case also the magnetic lines of forces are around that, like this only we have. Okay. So, but if you observe here the magnetic lines of forces, whenever these 2 current carrying wires are coming closer, then what happens there is, these magnetic lines of forces gives the direction of the magnetic field in the upward direction, whereas this one it is showing in the downward direction. See means whenever if you are taking the magnetic lines of forces here upwards, the other magnetic lines of forces here downwards, like this. As the pointing direction, one is upwards, another one is downwards, they are acting like unlike poles, that is because the direction is one is in the opposite direction here. Okay. As they are acting like unlike poles here, both the wires here actually starts attracting each other. So means when you are taking any of the 2 conducting wires which is of taken, okay, in the same direction of the current, which is taken in the same direction of the current, then the force acting between them is a repulsive force is acting. Means if this is the wire 1 carrying the current I1 and this is another one taking the current carrying I2, then the magnetic fields which are taken here as we seen, those are of anti-clockwise both the cases, like this. Then at this particular region what happens there is, the magnetic lines of forces directions are different in directions, that is one is pointing towards downwards, other side it is pointing upwards here. Because of due to that, then what happens there is, both the current carrying wires attract each other, means the current carrying wires are going this one this direction and another one this direction. They are slightly bending towards each other because of due to attraction, that is. Like this, by using the grip rule, we can find when you are placing 2 current carrying wires closer to each other, maintaining some distance between them, so that there is a force of attraction is acting between the 2 current carrying wires here I1 and I2, and both are attracted each other. So that is why they are bending towards each other here, like this. If you are taking the same current carrying wires, but in opposite direction if you are taking, means one of the wire the current carrying is upwards, that is of I1, and the second wire you are taking which is going downwards, which is I2, that is. See, the direction of current in the first case is towards upwards, like outside the plane, out of the plane, that is, whereas the second case we are taking that into the plane which is towards downwards, that is. Then according to the thumb rule, if you apply, as that is out of plane here, if you are curling the fingers like anti-clockwise direction here, so the direction of the magnetic lines are like this. Whereas in case of the second one, actually here as it is pointing downwards, means into the plane, that is. That's why in the case of second wire, now the current carrying wire we are having like this, the magnetic lines of force are acting. Means that is like a clockwise direction we have, so that the magnetic lines are going like this. But if you observe here in that plane, the magnetic lines of forces which are coming closer to each other here, they are having the same direction is present. Both are going upwards. Means the direction at this point, the magnetic field is upwards, and here also upwards. Means they both are acting like poles here. As both cases the direction is the same, they are acting like poles. We know that like poles repel each other. So that's why in this case what happened there is, the magnetic lines of forces are pointing the same direction, then the current carrying wires both are repelling each other like this. This moves this direction and that moves that direction here. So there is a force of repulsion is acting in both the cases, okay, like this. So whenever if you are taking both the currents, if both are taken in the same direction, we observe that following the grip rule, both are coming closer due to attraction. But whenever if you are taking both the currents, one is taken upwards, another one downwards, here we are getting both the currents are moving away from each other, which is repulsion takes place. So, but most of the cases in our competitive exams, they will give these conducting wires, sometimes 2 at a time or 3 at a time they give. So, actually we already seen for the single current carrying wire, and we have seen if 2 wires are given, how they are acting. Now we are taking as an example, here I am taking 3 conducting wires here, of which total 3. Okay, which is I1, I2, I3. Total 3 conducting wires we are taking. So that the direction of current, let us suppose for the first 2 like this. This one upwards and this one downwards and this one upwards like this. Then in this case, how the force is acting we will see. Now actually here the direction of the current is upwards, means let us assume that is like out of the plane. Whenever it is out of the plane, then the direction of current around that is like anti-clockwise, that is like this it comes. Whereas the next conducting wire, as it is pointing downwards, here we are having there is a force is acting between them, so that is like into the plane, means anti-clockwise, anti-clockwise becomes clockwise, that is. Okay, as it is going into the plane that is of clockwise, like this it rotates. So, if you observe here between I1 and I2, the direction of magnetic field is in the same direction. The magnetic lines are going at that point in the same direction. That is why I1, I2 start repelling each other, means that force is acting between F1 and F2 is like this. Then if you are considering for the case of I3, and again if you see between I2 and I3, the direction of current is in opposite direction. For the case of I3, the force is that current is going upward direction, that is, which is like out of the plane again. As it is going out of the plane here, again the magnetic lines of forces around that are like anti-clockwise direction, that is like this. But again if you observe between I2 and I3, here the magnetic field is pointing towards downwards at this point, this side also downwards. As both are going downwards here, the direction is the same. So, that is why between these two, again we are having a repulsion takes place there. So, which means both are moving away from each other. This F3 here and this side also we are having F3 is acting. Like this we have. So, means between these two repulsion, So, that is why this middle one, the net force acting on the second one. Okay. So, it is acting on both the directions here. Like this the force is acting from the either end, because this one repel this one and this one also repelling. So, that is why this moves this direction, this moves this direction. Whenever if you are taking the same strength of the current passing through all the 3 wires is the same, then there is no movement is present between I2 here. Okay. The I2 remains in the middle only. Like this, if 3 current carrying wires are given, we can find the net force acting on the wire there. And for suppose if you are taking all are of same direction, if you are taking going upwards, and second case also upwards, third case also upwards, then I1, I2, I3. Again if you see I1 for the first case of wire, that is going upwards, which is like out of the plane. As it is going upwards out of the plane here, the magnetic lines of forces around that are like here anti-clockwise direction, going up here like this. And whereas in case of I2 if you take, those are like anti-clockwise direction only, because the direction of current is also again upwards here in this case. So that is why here and here and here, all the 3 cases we are having the same anti-clockwise direction is coming. As here if you observe the magnetic force acting here, here the field is going upwards, here the field is downwards, here the field is upwards, here the field is downwards. So between these two here we are having a attraction takes place, that is why here it attracts like this. But if you consider the third one, that is also actually the field direction is opposite to each other, that is why this also start attracting and this also has to move this direction, means from both the sides both are pulling the second one here, and depending upon which force is acting more, that side this second one will move there. If both you are taking all the 3 of same strength of current is passing there, then the number of magnetic lines around this is same, the magnetic strength also remains same. So that is why here what happens there is this wire is not moving to any of the direction. Okay. Like this we are having in case of single current carrying wire you can take, 2 current carrying wires you can take, and even for the case of 3 current carrying wires also we can take. Now we will see these magnetic lines of forces whenever they pass over any of the conducting wire here. Okay. So let us suppose here the magnetic lines are coming like this. These are the magnetic lines of forces. If these magnetic lines of forces are passed over a particular area, like say for example like this, a conducting wire, a cylindrical conducting wire you are taking. Okay. Now here if any of the magnetic lines of forces, if they are passed over any of the conducting material, we call that as flux, which is called magnetic flux. It is called as magnetic flux. Magnetic flux is nothing but the number of magnetic lines of forces passing over area. The number of magnetic lines of forces are passing over an area, that we call that as magnetic flux, represent with phi. Represent with phi, that is. Now these magnetic lines of forces whenever they are passed over any of the conducting materials like a copper wire, any of that we are taking, then what happens there is as the magnetic flux is acting, this is equal to B into A, okay, of which the force, the magnetic lines of forces means nothing but the magnetic field strength here when it is passed over an area, then the flux is given by B dot A, that is. This is the case if you are taking completely perpendicular to each other here, means the magnetic lines of forces are entering onto the area which is perpendicular here like this. Okay. Then the direction of that area is given by its normal. So if you are taking normal for this area you are taking normal like this, n is the normal. Okay. If you are taking n here, the direction of the magnetic lines of forces and the direction of area both are in the same direction, the angle between them becomes 0 degrees. Means if you generalize the formula of our magnetic flux here, that is nothing but equal to B A cos theta, that is, where theta is the angle between the area there, area of cross section, and the magnetic field strength, the lines directions, that is, okay, the direction of magnetic field strength which is given by the magnetic lines of forces, and A means the area of cross section. Then the direction of area of cross section is given by our normal, that is. Now in this case, as the general formula is B A cos theta, to get this magnetic flux, here the direction of the magnetic lines of forces and the direction of the normal both are same. So that is why here the angle becomes theta is equal to 0. Then phi becomes b dot cos 0 degrees, that is. Then it becomes b dot a, because cos 0 is 1, that is. Okay. So, this is the maximum flux we have when you are taking the magnetic lines of forces are entering into the area perpendicular to the surface. Okay. For suppose general cases, if you are taking, most of the cases what happen there is, these magnetic lines of forces are coming onto the area here, making some angle. As it is making some angle here with the normal, if you are taking for this area of cross section here, the normal if you are taking, for example, at this point if you are taking the normal like this, then what happens there is, it is making some angle there theta. Then in those cases the magnetic flux is given by B A cos theta, that is. Okay. So, but now for this case, now we are taking, if that is going parallel to the area of cross section here. Going parallel to the area of cross section means, for example, if the area of cross section is like this, and now the magnetic lines of forces are passing over that like this, like this. In this case, what happens there is, if you take the normal for this area of cross section, that is going, taking normal is like this. The direction of normal is upwards and the direction of magnetic field strength is downwards here like this. Both are of perpendicular to each other we have, which is the direction of area of cross section and the magnetic lines which are crossing over that area here. That is why here the angle becomes again phi is equal to, as it is of B A cos theta, whereas the angle between B and A we got here 90 degrees, where theta is equal to 90 degrees. Then if you substitute cos 90, which is equal to 0, which is B A cos 90 degrees, that is, then which becomes 0, because cos 90 is 0. So, means the flux which is passing over any of the area, if it is going parallel to that, so that it makes perpendicular to the area of cross section to the normal here. So, that is why the magnetic flux passing over that is becoming 0. And when we have the maximum flux is present is, if it is going perpendicular to the area of cross section, which means it is like parallel to the normal we are taking for the direction of area of cross section, where the angle between them becomes 0 degrees there. So, that is why we are getting there a maximum flux is coming, which is phi is equal to B A into 1 B A, that is. This is called as magnetic flux. Okay. This magnetic flux which is of B into A, this we call that as SI unit is Weber. The SI unit of the magnetic flux is Weber. Okay. Now, from this we can define directly our magnetic field strength, which is B, that is. For example, for the case of maximum if you are taking, which is phi is equal to B dot A, then B is equal to, from this you can write phi by A. Okay. Which means nothing but per unit area how much is the flux it is passing, that only we call that as the strength of the magnetic field, that is called as strength of the magnetic field. So, this B we call that as magnetic field strength, that is called as magnetic field strength. Magnetic field strength is nothing but we are taking the maximum flux passing through an area, that area we are taking a unit area, that is, which is the magnetic flux passing per unit area, that only we call that as magnetic field strength. If the magnetic field strength is more, means more number of lines are passing over that area here. Then if it come to the case of units, here if you see for the case of that B, as B is equal to phi by A, where phi is Weber and A is area, which is of meter square. That is why here the unit for this magnetic field strength is Weber per meter square, that is. This Weber per meter square only we are calling that as Tesla, that is called as Tesla, or simply you can write that as T, like this, Tesla, that is. Weber per meter square, or that is called as Tesla, that is. Now we are seeing, now we are taking any of the conducting wire inside a magnetic field here. For example, like this, a current carrying wire which is going up. Now we are taking inside a magnetic field, this one. Then we already know that as the magnetic field here coming here, which is the magnetic lines of forces are coming here perpendicular to the current passing there, then what happens there is on this one, now here following the right hand rule there, of which the direction of current is upwards, and here the force acting here, the magnetic field strength is there, so that there is a force is acting. Now, for suppose if you are taking in this case, as the direction of current is upwards, of which we are taking the forefinger in the upward direction, and the direction of the field strength is, which is of middle finger, is towards that side. So, means like this, then the thumb represents into the plane here like this. Okay. So, means here in this direction of the current which is going upwards, now we are having the direction of the current, the direction of the force acting is into the plane here. Now, let us suppose I am taking one more wire here, which is other side to the downwards here like this, and again the magnetic lines of forces passing for this also in the same direction you are taking like this. Then what happens there is, as we are changing the direction of the current, this time it is downwards. So, again following the same rule, so that this we are taking towards downwards, that is, and the magnetic lines of forces acting are in this direction we have. So, means this middle finger again we are taking in this direction, and this forefinger it is acting downwards here like this. Okay. Then the thumb represents it is out of the plane to you. Okay. So, first case we are seeing that if you are taking the current there upward direction, and we seen that the current direction, the force acting is towards inside, and in this case the force acting is outside, that is, because the magnetic field strength that is going there is downwards, so that the field direction is towards me like this. So, that is why this thumb represents which is towards outside, that is, means here the force is acting inward, here the force is acting is outward. Then if you join this one, both the wires like a circular rectangular coil like this, then what happens there is, one force is acting into the plane, one force is acting out of the plane, which gives you two equal forces. As we are taking the same current is passing through the complete wire here, then what happens there is equal amount of force only acting there. But these two forces which are acting, first case F1, second case F2. Now, here this force is acting into the plane there, and this is acting out of the plane there. As one force acting into the plane, another force acting out of the plane, slowly this rectangle coil starts rotating here. Actually, this is the basic principle actually we have for the working of electric motor, that is. Okay, that is about electric motor. So, which means when you are taking a rectangular coil having the direction of current is in different directions, one is upwards, another one downwards, but here when the current is passing at this part, means let us suppose this rectangular coil is A, B, C and D here, then AB part the current is entering here, the magnetic field strength and the current here is perpendicular, and in the same way for the case of CD also, here the angle between them is perpendicular here. But whenever if you are taking for the case of BC part, here the magnetic lines are passing over that, which is having a minimum flux is acting, where the flux is becoming 0. As the magnetic flux is becoming 0, there the force acting there is also becomes 0. And not only that, even for the case of AD part also here, as it is of anti-parallel here, so no flux is acting there. So, that is why here in this case also the force acting becomes 0, that is. So, whenever if you are taking for the case of AB and for the case of CD only, we are having the forces are acting, whereas in case of BC part and AD part, even though the current is flowing there, there is no magnetic forces acting on AB and CD. Now, by using the same principle, now we are going to explain how a electric motor works. Okay, how an electric motor works. Actually, inside that electric motor, we are having like this, a rectangular coil is present, a soft iron core rectangular coil is present. That only we call that as armature, that is called as armature, that is. Now, this armature actually it is connected to a battery here. Okay, that is connected to a battery. So, that here the current is passing through that coil here like A, B, C and D. Okay. So, the current is passing through that one like this through ABCD, that is. Now, what we are doing is we are taking a magnetic field here. So, this side and this side having a north pole and a south pole here, means the magnetic lines are going from this end to this end. Okay. So, inside we are having the magnetic field is crossing over that wire here, and that magnetic field actually here for the AB part coming perpendicular, for CD part also coming perpendicular, for BC part that is coming parallel, and to the AD part also it is coming parallel to that one. Okay. Now, what happens there is, as I said earlier, here we are having a couple is generated which causes the rotation for the coil. So, for example, if this is the coil, and this coil if you are taking that inside the magnetic field there like this, then what happens there is, as the force is coming, as the magnetic lines are coming perpendicular to that, then what happens there is, it causes some force on this one. That force actually by using that right hand rule, now only we decide that that is going into the plane, because the magnetic lines of forces are coming like this in this direction. Now, as they are coming in that direction, we have to take that middle finger in that direction, so that the current for the case of AB part which is going upwards, then the force acting is inside, means it is pushing this coil. If this is the coil, this force is pushing that at the AB side there into that, and at the same time the other side which is of CD part if you are taking, as there is a change in the direction of current is there. Okay, before the direction of current is upwards, so the force acting is into the plane. Whereas to come to the case of other side there, where the CD case, the current direction is towards downwards. So, that is why this time the force acting is out of the plane we have. So, that is why here if you are taking this coil, at one edge we are having the force in this direction into the plane, the other side the force is acting out of the plane, that is. Then what happens there is, as two equal and opposite forces are acting on the same body here, then slowly here it start rotating here. This becomes like this. Okay. So, means here this coil start turning here, so that AB is going towards the south pole side and CD is coming towards this north pole side, that is. Okay. Then what happens there is, as whenever it completes a half rotation here, for example, if this is the coil, or you can take the coil like this, let us suppose A, B, C and D here, then AB side as we are having the current is going upwards, as I said the force is acting here like this. Then at the same time here we are having the force is acting, then the force will come outside like this, then it creates a couple and it starts rotating like this. Then whenever if half rotation is over, if you observe, as the magnetic lines are like this, that is going parallel to that one, so that what happens there is, whenever if it is the half rotation is over, means the coil is like this. This is the north pole and this is the south pole, and now the coil becomes like this. Okay, AB and CD, the coil is coming like this, which is coming straight like this it comes. Then what happens there is, as the magnetic lines are passing here, those are of going over the area of cross section here, which is again parallel here, which is again parallel. As it is going parallel, the force acting there is no force is acting, which is 0 force is acting. That is why here, as there is no rotation is present because of due to the magnetic field here, but here we are having the rotation because of due to inertia of motion. As the body is in motion, it continues to be in the motion here, because of due to that inertia the coil turns and finally it comes to the other side, means that AB is coming to the other side here. Then finally after that half rotation is over, then what happens there is, this coil in between that north pole and south pole, how it comes is like this. Okay. But here if you see that AB is going to the other side and CD is now this side like this. Okay. But see, if you observe, the direction of the current in the AB is upwards there, and the direction of current in CD is towards downward there. Previous case, to the north pole direction, that is the current passing is upwards, to the south there the current carrying is downwards here. But now after the half rotation is over, that AB part actually it is on the south pole side, and that CD part which is towards the north pole side is coming. Then what happens there is, again there is a change in the direction of the forces comes, because this side we are having a downward direction which is into the plane, that side we are having out of the plane we have. If out of the plane is there, the force acting is towards inside, and here the force acting is outside. Because of due to that, the coil starts returning back. It is turning backside here. It is reversing back. Means, for example, like this. If you are taking this is the coil, whenever the half rotation is over, going like this, because of due to inertia, it comes up to here. Now, as there is a change in the direction of the current is there at the south pole, it is going up now. Then what happens there is, here now the force is acting towards inside there, and here the force is acting this side there. That is why again it comes back like this. So, means in here in this case the direction of the rotation is like this, we have half and half like this. Okay. So, because here the direction of the current, if you observe there, continuously it is changing. At here the north pole side it is towards upwards, this side we are having downwards is present. But in case of motor, actually we are having a complete rotation is present. So, that is why to get that complete rotation, we have to add a separate one, we call that as split ring, which is acting like a commutator here, of which we call that as split ring. Okay. So, means like this, a split ring is added. Okay. So, that to this split ring, now we are arranging two brushes there, B1 and another side B2, that is like this to this split ring. Now, this B1, B2 brushes are now connected to the battery there like this. Now, what happens there is, whenever if the split ring starts rotating here like this, as it is in contact with B1, B1 is now acting like a positive terminal and B1 is acting like a negative terminal. Whenever the split ring starts rotating here, now that ring actually touches the B1 here, so that as B1 is having a positive terminal is there, the current going is upward direction here like this. Whereas B2 side we are having that CD is present, of which that brush it is in contact with the brush B2, of which we are having a negative terminal is present for that. So, that is why the current is entering into that B1 here. Now, whenever the half rotation is over like this, then as we are talking about the case of brushes, those brushes are fixed here with B1 and B2, where B1 is acting like a positive one, B2 is acting like a negative one here. And again towards that B1, even though that CD comes this side, then the direction of current won't reverse, it remains the same, because always positive terminal the current is going up here, and here the negative side the current is coming towards negative. Then the split ring which is acting like a commutator, whenever it turns this side, then it is now coming in contact, this CD part is coming in contact with the positive terminal, and that another part AB part it is now in contact to the negative part here. So, that is why here the direction of the current always towards the north pole side there, that is towards upwards, whereas to the south pole side that is always downwards only acting. So, that continuously the force is acting for the north pole side into the plane, for the south pole side out of the plane. So, that is why here continuously the force is acting in one particular direction, this side it is coming inside and this side it is going that side, so that the rotation is over. And again the force is acting this direction, this side acting that direction, again over, like this continuous rotation is coming like this. Okay. This only we call that as a DC motor, this is called as DC motor, whereas DC motor means that is called as a direct current, DC motor. DC motor means direct current. Okay. DC means direct current, where there is no change in the direction of current, that we call that as a direct current. Where there is a continuous change in the direction of the current here with respect to the time, periodically there is a change in the direction of current, like the previous one we see, that you call that as AC current, this is called as DC current, that is, whereas DC means direct, AC means alternate, that is. Okay. So, like this we can get a continuous rotation there by using a split rings which are connected to the brushes here. Now, we seen about that electric motor, how it works depending on this right hand rule there. Okay. That electric motor actually works on the principle that electrical energy we are supplying here, which is the current passing, it is converted into mechanical energy. Because of due to that induced magnetic field is there, it starts rotating. That rotation only we call that as a mechanical energy, that is. So, that is why the electric motor principle is converting electrical energy into mechanical energy, that is converting electrical energy into mechanical energy. Now, we are seeing the reverse process of that. Means now till now the examples we seen is from the electric fields when there is a current is passing or when there is a movement of charge is there, around that we are having a magnetic field is coming. Now we are taking in the reverse, if there is a magnetic field is present, so that around that magnetic field now we are getting a electric field is there. Means by using this magnetic field now we are getting the electric current, induced current, that is, of which this is given by Faraday. Okay. So, that is what is called as Faraday's law, Faraday. Okay. Now, according to this Faraday's law, whenever if you are taking any of the conducting wire, but remember we are not taking a current carrying wire here, we are simply taking only a conducting wire, but this conducting wire we have to take, which is a closed one we have to take. When you are taking a closed closed conducting wire here like a circular coil, only a conducting wire, and whenever if you are taking a magnetic field or the magnetic lines of forces passing over that conducting wire here, say for example, if you are taking a magnet having a north pole and south pole like this. When you are taking this conducting wire there, which is a closed one across that bar magnet here, from the bar magnet we know that from north pole we are having the magnetic lines of forces are coming outside. Whenever these magnetic lines of forces coming outside, they are passing through this passing through this conducting wire here, then according to Faraday's law, if you are changing the flux of the magnetic lines which are passing over that current carrying wire, means for suppose if you are bringing this closer towards the conducting wire here, which is of the current coil there, then what happens there is an increase in the flux takes place, means there is a change in the flux comes, change in the flux we represent with delta phi, where delta means change, phi means the magnetic flux. So, when there is a change in the magnetic flux is there, then according to this Faraday's law, here a current is induced. That current only we call that as induced current. Induced current means when there is a current is there, immediately we are getting an EMF is generated inside that. That EMF we call that as induced EMF, that is called as induced EMF. So, see the statement again, when there is a change in the magnetic flux linked to a closed coil, if you are taking particularly closed coil. Okay. So, when there is a change in the magnetic flux linked to a closed coil, then according to this Faraday's law, current is induced, called induced current, that current is called induced current. And this phenomenon of inducing the current by using the change in the magnetic flux, that only we call that as electromagnetic induction of Faraday's law, that is. Okay, that is called as Faraday's law of electromagnetic induction, that is. Okay. As the current is induced inside that, we are having an EMF is there. Then according to this Faraday's law, whatever the rate of change of flux we have, means with respect to the time, how much is the change we are getting in the flux, all that is equal to the EMF produced. All that is nothing but equal to the EMF produced inside that coil. That EMF only actually passing the current through that coil here. Okay. So, according to the Faraday's law here, when there is a change in the magnetic flux linked to a coil there, here it is inducing the EMF, we call that as induced EMF, of which produces the current. That current we call that as induced current, that is, this is called as Faraday's law. So, means when there is a change of flux takes place, that change of flux is giving you the current here. Okay. Faraday gave only about the effect, which is when there is a change in the flux, he said there is a current is induced, but he did not give the direction of the current, in which direction we are having that current is present inside that coil. That is given by another scientist name called Lenz. Okay. Lenz gave the direction of the current which is coming inside that coil because of due to change in the flux. So, according to this Lenz law said when there is a change in the magnetic flux comes, and here if there is a magnetic flux is coming there, changes inside that current carrying wire, the direction of the current is such a way that he said it always opposes the change. Okay, see that again. According to the Lenz's law, if there is a change in the magnetic flux occurs linked to a closed coil, as the EMF is induced or the current is generated inside that coil, the direction of current is such a way that it always try to opposes the change. For example, if you are taking in case of this circular coil and we are taking a bar magnet which is coming closer, if you are taking as the north pole is approaching towards the coil here, then what happens there is, as it is coming closer, the number of magnetic lines passing through the coil also increases. As the number of magnetic lines passing through that increases, the change is increasing. Then the current which is coming inside tries to oppose the change. Opposing the change means whatever the change, increase in the flux there, the current coming inside that tries to decrease the flux. That is possible if the current is, as the magnet is coming closer, if you want to oppose the change, if you want to stop the magnet, then this coil is behaving like a north pole now. It is behaving like a north pole. Then north pole repel each other. So that's why here there is a decrease in the flux that takes place. Means if you want to act like a north pole here, then the direction of the current inside that is like anti-clockwise direction, that is like this. It is going to be like anti-clockwise direction, that is. Okay. So according to this Lenz's law, when there is a change in the magnetic flux linked to a coil is there, which is causing the induced current, the direction of the current is such a way that it tries to oppose the change. So that's why as the magnetic flux is increasing, that increasing is the change here. That's why here inside that magnetic field here, the coil is acting like a north pole, so that the direction of current is in the anti-clockwise direction and it is behaving like a north pole and it repel that magnet, so that it can decrease the flux. Okay, because the now north pole is approaching towards that, then magnetic lines of forces are more and more increasing. Then once if you are behaving like a north pole, it repel each other, then what happens there is again decrease in the flux takes place. Okay, like that here we can give the direction of the current in case of this closed coil by using Lenz's law, that is. So now from Lenz's law we got that there is a EMF is induced so that it opposes the change. So means as Faraday is given the mathematical form E is equal to delta phi by T, the direction of the induced current as it is against the change, then E we have to take as minus d phi by dt or d phi by delta T, or T we can take. Okay, means rate of change in flux is in the opposite direction we have to the EMF generated there or to the induced EMF there. E is equal to minus d phi by dt. Most of the cases in our competitive exams, how they will ask the questions is, for example, if you are taking the closed coil here, so that if a north pole is approaching towards that, so there is an increase in the current is coming there. There is an increase in the magnetic flux is there. As because of due to increase in the magnetic flux as it is approaching, here the change is increasing. So that's why it tries to decrease the change. Decreasing the change means here it behaves like a north pole as we seen. So the direction of the current is in anti-clockwise direction. For the same case, for suppose if it is leaving, means from this closed coil, now the magnet starts leaving that, which is moving away. If it is moving away, then what happens there is here as the decrease in the flux takes place. As the flux is decreasing, then the induced current here, it behaves in the opposite direction. It want to oppose the change. As the change is decreasing, it opposes the change, means it tries to increase the magnetic flux here. And how we can increase the magnetic flux is by acting this like a south pole here. As it is acting like south pole means the direction of current is in clockwise direction, that is. Okay. So symbol, whenever it is approaching, there is an increase in the flux. As the flux is increasing, the change is increasing, then the current induced inside that is opposing that change which is increasing. So that's why it tries to decrease that. It can decrease by taking the opposing that one, which is of same north pole which repel each other. Whereas whenever if the magnet is leaving, then the magnetic flux is decreasing. As the magnetic flux is decreasing, then what happens there is it tries to increase the flux, because this is acting opposite to the change here. So that's why it tries to attract that north pole by behaving this as a south pole, that is. So that's why the direction of current is in clockwise direction. And in the same way, if you want, you can take, even in this case, a south pole is approaching also. For suppose if a south pole is approaching towards that current carrying wire, sorry, towards that conducting wire there, then what happens there is, as it is approaching, here again the flux increases. Then as the flux is increasing, then this induced EMF try to decrease the flux, so that it behaves like repelling one. Repelling one means this behaves like a south pole now, like this, okay. And at the same time, if suppose if that south pole is leaving the surface, means leaving this area here, then in this case what happens there is, as it is leaving, the flux is gradually decreases, but the induced EMF which is getting inside that try to increase the flux. It can increase the flux by attracting that south pole, of which this behaves like a north pole, that is like this. So depending on the change in the flux, whether it is increasing or decreasing, opposite to that, if there is increasing, this tries to decrease that. If that is decreasing the flux there, and induced EMF try to increase that, so that there is a change in the direction of the current is coming here. This change in the direction of current according to the direction of the change in flux, this is called as a clock rule. That is called as clock rule. Whenever it is going in the anti-clockwise direction, means that is acting like a north pole, and whenever it is going like a clockwise direction, that you call that as a south pole, that is. So here in this case, in both the cases we seen that magnet is approaching towards the conducting wire there, or the magnet is leaving the conducting wire there. It need not to be every time the magnet is moving there. Sometimes we can take, for example, here we can take even the coil also move towards the bar magnet also. For example, this is the coil, and here if you are taking the magnet, this time the magnet, that conducting wire only going towards the magnet, and this is at rest, and maybe like this it is moving away, so that again the magnet is at here, like this. Or you can take even with the south pole also same, which is coming closer towards a south pole and which is moving away from the south pole also, like this. Then in these cases also same, whenever it is approaching towards the magnet there, then what happens there is an increase in the flux is there, so that it tries to decrease the flux, and it behaves like a north pole again, means like this, anti-clockwise direction. And at the same time, whenever it is moving away from that, then what happens there is a decrease in the flux comes there. So that's why it tries to increase the flux by behaving like a south pole here, so that the direction of the current, it is of anti-clockwise direction, that is of clockwise direction, that is like south pole. And whenever if you are taking, if the south pole is near to that and it is going towards that south pole, then it tries to decrease the flux, because the flux is increasing. So that's why it acts in opposite direction, behaving like a north pole, so that here, behaving like a south pole, because there is an increase in the flux. Then what happens there is, then the behavior is like a clockwise direction, that is. Then when case of this, it is leaving the south pole here, then the decrease in the flux takes place. Then what happens there is, here in this case we are getting a north pole is coming, means that is going in anti-clockwise direction, so that it can attract, there is a change in the increase in the flux takes place there. Like this, by moving the magnet or by moving the closed coil, in both the cases we are getting this change in the flux is coming, and when there is a change in the flux takes place, according to our Faraday's law, we are having that induced current is coming. That induced current is in the direction such a way that, from our Lenz's law, such a way that it is opposing the change of the magnetic flux. In that way, it is conserving the energy also, means Lenz's law actually it is a consequence of conservation of energy, that is. So as we are taking here the current here, which is about a coil or a conducting wire, that is. Now we can use our formula F is equal to BIL here. We already derived this formula before. F is equal to BIL, because there is a current carrying wire is there. Okay. Then as F is equal to BIL, according to our Faraday's law, we have that the induced EMF E is equal to delta phi by T, that is. Okay. Now, which means that here whenever the coil is coming closer, that is acting like a mechanical energy, that is as the coil, that magnet is coming closer. So, there is a work done is there, that work done W is equal to force into displacement, that is. Okay. According to our formula, work done is equal to force into displacement, that is. Here the force acting, now it is making the coil to rotate, which is of BIL, that is. Okay. Of which the force acting on that is equal to BIL. Then if it is BIL there, into displacement S is there, then W is equal to B into I into L into S, where that is of length into displacement, that is, that gives you area, that is, which is like area. Okay. Now, when you are considering that area, we can write that W as B dot A of I. Then here if you observe B dot I, which is the product of that magnetic field strength into area, that only we call that as a flux, which means whatever the work we done, that is nothing but when there is a change in the flux is taking place there into I, that is. Okay. Then if you are considering that is of power, how much with respect to the time if you are taking, then that power P is equal to work by time is equal to delta phi by T into I, that is. Whereas delta phi by T according to our Faraday's law, that is nothing but equal to the induced EMF, that is, which is E into I, that is. So, finally, we got P is equal to work by time, that is of equal to the EMF into I, that is. But if you remember in basics of that current electricity, we seen that EMF is like voltage, the potential difference, that is. And here we got the formula that it is like EMF into current, which is like voltage into current I, that is, means the product of voltage into I, that is nothing but called as electric power, that is. This power is about electric power, and what we took is about the mechanical work done here, of which its mechanical power, that is. This mechanical power, that is. So, means obviously the mechanical power which is equal to work by time, that is equal to the electrical power which is equal to E into I, that is. From this it is very clear that whatever the work done we are doing mechanically, all that is converted into electrical energy. This is another proof that there is a conservation of energy takes place during this Faraday's law takes place. Okay. So, that is why here we got that mechanical work done is equal to E dot I, which is equal to electrical work done, which is equal to E into I. In place of that EMF, we got E is equal to, which is B dot A, where that B dot A is equal to here B into L into S, that is. So, means we got a new formula for this EMF, which is B into where A is equal to L into S, that is B into L into S. This is the EMF formula. E is equal to B into L into S, that is. So, as we got that E is equal to B dot A, where which is the EMF we are taking, where B dot A it is the flux change here, that we are taking per second, that is, which is of time we are taking per second, because that work done we are taking power per second there. So, that is why here we have to take per second, which is the time there. Okay. Then whereas length by time, that you call that as I, that is. So, which means E is equal to B of I into whatever the displacement we are taking, that is equal to S, that is. Okay. Where E is equal to EMF is equal to B into I into S, whatever the displacement it covers. Now, we are applying this electromagnetic induction, which is of a Faraday's law, now to electric generator, that is, which is the reverse principle like this. Mechanical energy is now converting into the electrical energy, that is. Okay. Mechanical energy converting into electrical energy, that is the working principle of electric generator, that is. Now, we are applying this Faraday's law to electric generator. Electric generator, electric motor. Okay. In both the cases the setup is same we have, of which again we are taking a closed coil, but this time we are taking a rectangular closed coil, that is. Okay. But the principle of that motor is actually we are converting their electrical energy to mechanical energy, but in this electric motor now we are taking this conversion of energy is from mechanical energy to electrical energy, that is, which means here we are taking the coil okay, that rectangular coil, and which is connected to the rings like this. Okay. Now, this rectangular coil is placed in between north pole and south pole. So that what happens there is a magnetic field is coming here from north to south, and as it is of mechanical energy, by using that mechanical energy, now we start rotating the coil here. Whenever the coil is rotated, let us say for example in case of AB to CD case. Let us suppose if ABCD is the rectangular coil, initially that AB is closer to the north pole, that is means there is a flux is coming inside here like this, and the distance is very less, means where there here in this case the magnetic flux is more we have. But once the coil starts rotating, means for example if this is the coil here, so that I am taking the coil here like this, whenever it starts rotating, means let us suppose it start rotating like this. Then what happens there is, initially this part AB part is closer to the north pole, so that whenever it comes like this, the distance between the coil to the north pole is increasing. As the coil to the north pole it is increasing here, there is a decrease in the flux that takes place. So, there is a decrease in the flux causes decrease in the EMF here, decrease in the flux here. So, there is a change is coming into the flux. Then according to the Faraday's law, immediately as there is a change in the flux that takes place, immediately there is a current is induced in the coil. Okay. As there is a change in the flux there, as this is of north pole it is, then there is a change in the flux, it tries to behave like a south pole here. Then as it is acting like a south pole, so that it can attract there, again there is an increase in the flux takes place there. But here if you observe, whenever the half rotation is over, okay, now it goes to the other side we are having a south pole is present. Then immediately south pole repel each other, then what happens there is, now the coil turns back like this, as because of due to south pole repel each other, as the coil is now coming back here. Again if south pole as it is of going there and it is coming this direction, then what happens there is a decrease in the flux comes. As there is a decrease in the flux comes, then the produced EMF, induced EMF, that is it tries to increase the flux by making into a north pole here. Then as it is coming into a north pole direction here, the current here again that is coming towards this side, and this side again we are having a north pole is acting. Then what happens there is, again it tries to move away from that because of due to repulsion, again it start coil going to the other side. Then whenever it is going to the other side, again there is a decrease in the flux takes place, decrease in the flux, then induced EMF try to increase the flux there. As it is repelled from the north pole here, it tries to be like a south pole. Then immediately south pole, other side also we are having south pole is there, again it repel. So finally what we understand is, this coil start rotating here like this half and half, means there is a continuous change in the direction of current takes place, which is sometimes it is of clockwise direction and the other time it is like anti-clockwise, again clockwise, again anti-clockwise. So there is a continuous change in the direction of current takes place with respect to the time, that only we call that as AC current, alternating current, and this setting we call that as AC generator, that is called as AC generator, because here the current is changing, the direction of current is changing with respect to the time periodically. So that's why it is called as AC generator here. Okay. Now here, as there is a continuous change in the direction of current between A, B, C, D there, now we are making this AC generator into a DC generator, which means we do not want to change the direction of the current. Again we have to use, just like the previous case, a split rings are arranged here. Instead of taking both the rings there, here I am taking only one ring again. Okay. Of is just like the previous case, now we are arranging a split ring, that is like this. Then again we are having here two brushes are there. Okay, B1 and B2, this is B1 and this is B2. Now these brushes are now connected to the resistors there, means to our any of the electronic appliances like this. Then what happens there is, when you are arranging the mechanical energy there, when we are having the mechanical energy which is rotating the coil, so that there is an increase in the flux is coming. For example, for the case of AB part, as this is moving away, then there is a decrease in the flux takes place. Decrease in the flux causes, there is a change here, that change causes the induced EMF there, that induced EMF tries to attract that, which is behaving like a north pole, that is, okay, which is behaving like a north pole, that which is behaving like a, in this case AB part you are getting a south pole is there. So that what happens there is that is going like a clockwise direction current. Okay, but once it goes to the other side here, that side we are having it is connected to the B2 there. So that what happens there is, even though that AB goes to the other side also, there is no problem we have, because on that side of AB part, on the side of the north pole, we are always having the same type of current is coming, because this side if it comes here, other side we are having a south pole is present, then south pole repel each other, and again it behaves like a north pole. So, because as there is a repulsion takes place, it moves back here. So, that what happens there is a decrease in the flux. Decrease in the flux causes here it tries to increase the current by the induced current, that is. As the induced current is try to increasing that, then the direction of current is like a north pole here, which is of anti-clockwise direction. That anti-clockwise direction current it is coming at B2 side there, and here always the clockwise direction current is coming along B1 side there. So, that is why here always to the B1 side we are having the same type of current coming here, and whereas in case of whenever the coil turns to the other side, it is coming here the anti-clockwise direction, which always we are having that anti-clockwise is present. In that way we can get the current which is passing inside this coil always remains as same when you are using this split ring commutator. Okay. In that way we are getting a DC generator, so that without change in the direction of current we can get the induced EMF. If you are taking a graph here, for example, if you are using a AC generator there, then what happens there is to the EMF with respect to the time if you are taking with respect to the EMF. Initially the EMF is more whenever it is closer, so that is why here it is increasing gradually. But whenever the coil starts rotating because of due to that mechanical energy, then what happens there is a decrease in the flux changes. So, there is a decrease in the flux comes. Okay. And not only that, here what I said is that clockwise is now becoming anti-clockwise there, means there is a change in the direction of the EMF is there, going down and again going up. And whenever it comes closer to the other side, means again there is an increase in the flux that takes place. So, again the graph going gradually increasing there like this. So, like this, whenever if you are taking the case of EMF here, gradually increasing, decreasing, increasing, decreasing, and the direction of current also if you take, one side we are having a clockwise there, other side we are having a anti-clockwise is present. Whereas, if you are taking for the case of like this our DC motor, if you are taking, how the graph comes is, in this case, after completing the half rotation is over, there is no change in the direction of current, because gradually the EMF is increases whenever if there is a change of flux comes. Whenever it goes to the other side, again the repulsion takes place, again there is a decrease in the flux there. But even we are connecting to this commutator there, which is of the split ring is present, as there is no change in the direction of current, again we are getting the curve, same curve only we are getting, like this we will get. Okay. And again after completing one rotation, again like this. So, there is no reverse current is taking place. So, that is why here in case of this DC motor, we are always getting only the positive curves only coming, whereas in case of that AC generator, here we are having increase in the flux, and there is a reverse in the direction of current, and again coming back to the direction, again reverse in the current. But in case of this DC, there is no reverse in the direction of current here, because always the direction of current is in the clockwise direction one side, other side it is anti-clockwise direction. Okay. Like this the AC generator works, like this DC generator works. Okay. So, this generator works under one principle, that is of converting the mechanical energy into electrical energy. So, in this electromagnetic induction part, what we seen is how the magnetic fields we are getting because of due to the electric field, and how we are getting the electric field due to magnetic fields here. Okay. So, when there is a current carrying wire is there, we already seen that the magnetic lines are coming, which are closed curves around the current carrying wire there. And after that we have seen that how the magnetic lines of forces are changing depending on the strength of the current in different cases, like straight conducting wire we seen, after that circular coil we seen, after that taking into a solenoid which is a strong electromagnet we seen. After that we applied that to the case of this electric motor there. so that there is a increase in the flux there, decrease in the flux we seen in case of this generator also there. Okay. So that finally we got that magnetic lines of forces. Okay. These magnetic lines of forces are coming depending on the current flowing there, and after that we seen how there is a force is acting on any of the conducting wire you are taking, and after that we seen by applying that we are getting that working of motor is there, working of the motor, and after that according to our Faraday's law, which is of getting the electric current from the magnetic field, induced EMF from the Faraday's law, and after that depending on that direction here, Lenz give the direction of the induced current. Based on that Faraday's law and Lenz law, we explained how the electric generator is working there. This generator we also call that as dynamo, that is. Okay. So, like this we have seen how the electric motor is working there, converting here electrical energy to mechanical energy, and we seen here the generator which is in reverse case mechanical energy is converted to electrical energy, that is. Okay. So, like this in electromagnetic induction, okay, we can get one field to another field here. But in all the cases always electric and magnetic fields are always perpendicular to each other.